This carbon, what's the hybridization? Careful, it's sp3. The lone pair goes into a hybrid orbital. But what can it do? Resonance, and it can put that pi, or those 2 electrons, that lone pair, into a p orbital. And so that does contribute. So we do get those 10 pi electrons. Right. The rest of them is where I would say it gets a little bit trickier. I think the first one you guys should have got. First one was
anti-aromatic.
Oh, maybe that was one of the ones I would have labeled that as anti-aromatic as well. All right, as far as our pi system, we're only looking at the double bonds. Why do we not count the lone pair?
Because it's that trigonal planar. So
Perpendicular. The geometry around that carbon is trigonal planar. Those pi electrons can't, or sorry, that lone pair can't shift into the pi system, so we can't do that resonance. Okay. Next one.
does it twist to avoid the aromaticity?
If you count the oxygen as part of the system, I would agree it's anti-aromatic. That oxygen's lone pairs aren't officially in the pi system yet. Okay, the only way it would shift in is if it's allowed to do resonance. Well, the only way it would be allowed to do resonance is if that orbital overlapped with the rest of the pi system. If it did that, it's anti-aromatic. Is that stable? No. So what does it do? Tweaks its geometry a little bit such that you end up getting the non-aromatic system. Okay, so the oxygen's electrons don't count. So this is where it gets into that trick question. I would come up with the same statement. So this is exactly what the slides describe, is this is non-aromatic as being the correct answer. And they say, okay, well, the oxygen decides to tweak its geometry to prevent that. Well, what happens in this case? This looks an awful lot like the octa something or other, right? Okay. And in that case, what did it do? It puckered so that it was no longer aromatic as well. So can't we shift all of these p orbitals out of the plane so they're no longer within overlap, and now it's not anti-aromatic, it would be non-aromatic. So that non-aromatic, anti-aromatic line, that's why I said you got to be careful, it can be kind of a trick question. So depending on what they're looking for, you might get this, oh, it puckers, so it's non-aromatic, versus, oh no, it's staying flat, so it's anti-aromatic. How would I delineate that on the test? I would go through and say, this structure is planar. Define it. Okay? So if we go through and say step 2 or problem number 2 is planar, that oxygen is now forced into that proper geometry, which means it's anti-aromatic. Okay? So we have to watch out a little bit with the geometries and what can happen in the structure kind of puckering to avoid that unstable anti-aromatic situation. Okay? Questions about that? Yes?
What really is the difference between non and anti when it comes to the chemistry? Why is it so important to know the distinction?
So anti shows that we have overlapping p orbitals. Okay. Those overlapping p orbitals can potentially do interesting chemistry. Okay? For instance, that structure could fall apart in I'm going to say the name wrong, electrocyclization reaction. Okay, which we looked very, very swiftly at. Remember we looked at Diels-Alder before we got into Diels-Alder? Talked about, pericyclic, there we go. Okay. We can see reverse pericyclic reactions. We're in a pseudo-cyclic state right now. The reverse would be it opening up and saying, screw this, I don't want to be a circle. Okay. So it does change a lot of the chemistry. Whereas if we got rid of all of the pi bonds, now it's non-aromatic, it's not going to do anything. Okay, so there is a subtle distinction between them. Sometimes you get a little more chemistry, sometimes you get a little less. Last one.
Non-aromatic.
This could go back to your non versus anti, right? Non, if you count everything as planar, or sorry, if it puckers, if it's planar, you'd get the anti, right? Did I do that right?
No, I think the sp2 just stops it from being, you don't have a conjugated pi system.
What do you mean you don't have a conjugated pi system? If this puckers out of the plane, you don't have a conjugated pi system. If this molecule is planar, every atom is sp2. Your p orbitals do have the potential for overlap. We don't have, yeah, So we would have 2,4,6,8. That puts us in an anti-aromatic situation. The only way we get non-aromatic is if the structure puckers and prevents the p orbitals from aligning with each other. Are you trying to suggest something else? You both seem to agree with that statement that you guys were
I
making.
thought there's a very similar slide showing this situation, a couple back.
Okay, let's go back.
I could just be,
I could easily be wrong too. I think those are a bit rude as far as the parallels. It may have been. Whoops.
When we talk about the nose.
So here we've got the anion.
Yeah. Yeah, we talked about, oh, there you go.
With the penting.
Yeah, with the penting, we have the.
Oh, and yeah, I called this anti-aromatic, yeah. So based on assuming it's planar, we'd call that anti-aromatic, right? Isn't that what I said?
I thought we called it aromatic. I'm pretty sure.
This I called non, for sure. This I was pretty sure I called anti.
Okay, I may have just mixed the two up.
Okay. They're very similar in structure. I should tweak their structures a little bit, make it less possible to overlap. But just in case, let's go through and clarify that. This one here is your non-aromatic. There is no way that one can be aromatic or anti-aromatic because of the hybridization of that carbon being sp3. When we shift to this one here, that carbon up top is now sp2, which means there is a leftover p orbital. That p orbital, if forced into the planarity of the ring, now allows resonance all the way around, and we'd satisfy rule number 1. Rule number 2 would come in, and we'd have to look at the number of electrons. The number of pi electrons in this case is 4 pi, which doesn't match our Huckel's rule. We'd be looking at anti-aromatic. So yeah, if I goofed that earlier, I apologize, but
No, I
that's
just mixed them up.
that's the way that one should be. I know, sorry, we're going to get blinded again as we go through it fast. When we get back, this one here should be, oh wait, it was the last one, right? We've got 2, 4, 6, 8 pi electrons. The sp2 hybridization on that does give us a p orbital that we could push electrons through. So we do satisfy rule number 1 if we assume this thing planes out. Okay. Rule number 2 is we have to have that proper number of electrons. We don't, so we'd be looking at anti-aromatic. Everyone clear?
I think the homework does it where it does pucker though.
Yeah, so that's going to be the
Because
problem you're going to
that's
have to
why
watch for
I knew to call that non, because I've already done all.
because of the puckering. Yeah.
Because if you, it'll get marked wrong, and then it gives this long
That-
explanation
yeah.
of it will pucker.
So watch out for that when you go through and do the homework. As I was going through the slides, I saw that note with how to arrange them, and I thought, oh, that's going to be a nightmare to sort out. Because as far as you guys being able to predict, as far as I know how to predict whether or not it puckers, if it's given the opportunity, it's going to get away from the anti. So I would call it non-aromatic. But that same argument would then go apply with the very first one, and that very first one very clearly is stated non-aromatic. Or sorry, anti-aromatic. So that's the issue that I see popping up. I will try and go back through the homework. Do you know how many problems are like that, where you get that issue? Hopefully it's only 1 or 2.
It's like 3 or 4.
Okay, I'll go back through and try and pull questions.
I think it only
Or at least
takes
just
off
give
like
points.
2% though. Because
Okay.
it becomes obvious because there's only 2 answers, so.
Okay. Yeah, I will go through and take a look at points on that. So if you can send me an email on which ones are the problematic ones, I'll zoom in faster to it and fix that as far as points go. Okay? So for sure, when I ask on the exam, I'll specify you cannot pucker this structure. Or I'll give you the opportunity to say, hey, this structure can move, what happens? Okay? More than likely, because of that confusion, you'll see that as a short answer, not as a multiple choice. Questions? Okay. So the rest of this chapter is looking at the reactivity of the benzylic position. After that, we'll move into whatever the next chapter is, 19, which looks at the reactivity of the ring itself. Okay, which interesting, because we just said the ring shouldn't react because it's super stable. Okay. We can make it react. So first off, the benzylic position, kind of the interesting things with that. It turns out that those positions, and they're trying to point to those, and I can circle that carbon or dot it as a red dot. Those positions become particularly reactive in a slew of different reactions because the benzene ring contributes to stability or chemistry around those positions. So if you make that carbon positive or negative, if it's positive, the ring can donate electron density out to that position, stabilizing the positive charge. If that position becomes negative, it can donate the electron density into the ring. Okay? So both contributions can change the overall chemistry at a standard, what would appear to be alkane position. So if we take just standard benzene, or even just a standard alkane, so we separate the two functional groups, if you will, away from each other, and we react them with an oxidizing agent, and in particular a strong oxidizing agent, nothing happens. But if we combine those two functional groups into one piece, we do see some chemistry at that benzylic position. Okay? So in this case, we put the two together, and we run the reaction, and what happens? You end up losing a whole bunch of different carbons at the end, and I have yet to find what happens to those pieces. All of those carbons get removed, and you end up fully oxidizing that carbon, the one remaining, okay, to the carboxylic acid. Okay. Like I said, I'm still working on trying to find an explanation for that. The best bet I've got is that you do a pseudo substitution with water. Okay, that position will react with chromium or the chromate, and then that can act as a leaving group, and it can do some oxidation. Once it's at the alcohol, it'll very quickly oxidize. Okay? That position needs to have at least one hydrogen. So if we look at another situation and go through and take a look at that carbon, no hydrogen, no reaction. Okay? So what would that suggest to you is the importance of that hydrogen? What do you think that benzylic position is going to act as? I would guess it's going to be acidic. Okay? So we could pull off that hydrogen, leaving a negative charge on our carbon. That negative charge could potentially react with the chromate compound, and that's at least my current hypothesis for how that would propagate outwards. Okay? Why would we assume that it's going to be acidic and not, say, basic? Okay, why would it not get rid of that, or not basic? Why would the carbon take the electrons from hydrogen and not the other way around? Why do we not expect something along these lines? A positive charge at that carbon. The counter to that would be H minus. The likelihood that we're going to kick off H minus, not so good. Okay. So more than likely, that hydrogen is going to make it act as an acid. The benzylic position becomes acidic. And then it's that carbanion that then does some chemistry with the chromium to go through and generate your alcohol, which then propagates out to your carboxylic acid. Okay? Just thought it was interesting and worth mentioning. You can also use permanganate, just because one oxidizing agent isn't enough to forget. We'll throw in another one. Permanganate, remember, has been used to react with double bonds before. We could use it in mild conditions with cold and dilute permanganate to generate the diol with an alkene. If we went through and we did it hot and vigorous with concentrated acids, we could end up splitting the alkene open into the carbonyls, okay, and potentially the acids as well. Similarly, that benzylic position will react in the presence of permanganate and fully oxidize as well to the carboxylic acid. Okay, so just kind of be aware that that is now added to your repertoire of chemicals. Why would the benzylic position be similar in reactivity to the allylic positions? Just talked about it.
Because
We get a resonance effect. Whoops, I didn't want that one. So we could go through, if we made sure that that position, said it acted as an acid, that negative charge could then resonate into the structure, and we've got a ton of different resonance options where we've spread that negative charge. Ooh, that was terrible bond angles there. I apologize for that. Push that into the rest of the structure, and we've got our negative charge, okay, delocalized across it. So that's if it acts as an acid. Could we have it act as something else? Okay, if you got the next thing that pops up, that should give you a big hint. What other chemistry can occur with alkanes? In fact, typically, what's the only chemistry that can occur with alkanes? Radicals. Okay, that position is very active for a radical reaction. Okay, because we have that hydrogen on there. If we bring in a radical and do our single electron transfers, that's supposed to be a single-headed arrow, and we can now generate a radical or resonance stabilized radical at that position. Okay, and you could go through and draw all those fun radical mechanism arrows. So we can go through and brominate at the benzylic position using NBS. Why do we use NBS and not, say, bromine? What does NBS supply? It supplies bromine. Why do we not just use bromine?
When you use, like, you mean a BO2?
Yep.
So
Why
you
not?
have the partial negative charges and reacts like that.
Yep. But we could bring in just Br, and with heat, that bond is polar enough that we could probably break that open and still get our radical bromination.
React somewhere else.
Bromine is fairly reactive and can potentially react with other things. Okay? NBS is fairly selective. It generates such a small amount of bromine that we really are only going to react at the most reactive position, which is going to be our benzylic position. If we added straight up bromine, that can react with the rest of the structure at other positions as well. Okay, so we want to limit those other side reactions by limiting the presence of that reactive species. So we'll use NBS instead of heat, or sorry, instead of Br2. Okay?
So the NBS goes for the tertiary carbon.
Yep. And why does it end up doing that? Because we generate the most stable radical at that position. So when you go through the radical mechanism, you pull off a hydrogen, leaving behind a radical. That radical needs to be as stable as possible. And you're going to see that most stable position be, first off, tertiary. And it's even better than tertiary because the benzene ring can stabilize that radical intermediate as well. Okay, so you get all sorts of contributions pushing towards that position being our bromination. Once it's been brominated, you can then go through and do all sorts of other fun reactions. You can go back and do your substitution reactions. SN1, how do we know that first one is SN1 and not SN2? Don't tell me because it says SN1, but that is a valid answer. Two big reasons. I can point to them.
No, it's just a tertiary.
Okay, you said it faster than I can draw it out. First off, that is a tertiary alkyl halide. That's a big reason why we're pushing SN1. The other reason, circled now, what is the nucleophile? It's a weak nucleophile. Weak nucleophiles also tend to push your SN1 reaction. Okay? In the case of the SN2, we know it's SN2 because it is a primary alkyl halide, and we're looking at a strong nucleophile. Okay. As long as we've got a leaving group, we can also go through and do elimination reactions. So there's two different options here. We could do it as an E2 with the alkyl halide. To do that, we need a strong base. We could go through and convert it into the alcohol and do the E1 if we so chose by adding in a strong acid. What's the role of the acid in the case of the E1 elimination shown? To do an elimination, we need to remove a hydrogen. So that would suggest base. Why can we use a strong acid? And in this case, why do we have to use a strong acid?
To make the water later.
We need a good leaving group. The acid is there to pre-activate the alcohol to act as a leaving group. Okay, so that goes back to our alcohol chapter. When are we done? 50? 55? 55. Good. We'll keep pushing. This slide just summarizes everything that was just addressed. I don't think anything on this is particularly, all that useful. I thought that the oxidation ones up at the top gave you a little bit more information. Okay. So the new piece of information as far as you guys are concerned is that oxidation can be your chromic acid. Since it's easier for me to write chromic acid, I'm going to write that. Or your permanganate, KMnO4, okay, for your oxidation steps.
PCC would react with that?
No.
Create an alcohol or just not react at all?
Won't react at all. You need a strong oxidizing agent. Okay? And now that I say that so confidently, I'm not positive on that. So I guess I should be honest there. I'm not positive there, but based on what I've read so far, at least the textbook's given you, saying chromic acid as a strong oxidizing agent, and the permanganate is added not cold and dilute, but hot and strong acids. So that suggests to me you need a vigorous oxidizer, okay, to go through and push that reaction. The alkane doesn't want to react on its own. Okay? Remember, your standard alkanes are pretty weak reactions. To get the chromic acid or the permanganate to react before, we needed something else there to kind of polarize and help initiate that. In this case, what we're really relying on is the extra reactivity because of that resonance from the benzene ring. So I would strongly guess that you're looking at chromic acid or the permanganate pushing that. Okay. The other one that might be kind of new to you, sorry, was that a question?
It doesn't warm permanganate open up a ring?
It opens up an alkene ring. Okay, so you got to be careful with that. It'll react with an alkene. This isn't a standard alkene. Why is that double bond not a standard alkene? You get the resonance. I mean, if you want to think about it this way, the permanganate comes in to react with the alkene and it moves. So, well, shit, okay, I'll go over here, and it moves again, and it moves again. So the permanganate can't really get a hold of it long enough to do that pop open with the alkene. The other one that's potentially new for you guys would be your radical brominations. Okay, again, that should be review, but it's not really. NBS and light. Okay, actually, I think in this one they said no light. They said heat. So you could do NBS and light or NBS and heat. Okay. The rest of those on that chart are standard. So, kind of curious where I am in the slides. So, what kind of reagents do you think you could throw in on this? Oh, we still got that reduction.
NBS.
So that first one, why do you say NBS?
Because it reacts with tertiary carbon.
I would take it further than that. The chemistry is happening around what type of a functional group there. Okay, we could call it benzylic. I would probably even push to alkane. Okay, but benzylic is valid. The only way we can get that to react is in a radical type reaction. Radical, or we oxidize the crap out of it. So in that first step across, NBS is going to be our best option. Why do we do it at both positions? That one's a little bit harder to tell. Both of them are equally reactive, so which one reacts first, who knows? Okay. In this case, we could probably say you're just adding an excess of it. How do you move to the next one? Moving rightwards, that is.
Doing elimination reactions.
Okay, so the first step would be to identify that we're running an elimination.
This
Okay. To do it, what do we use? Okay, I kind of like what you're saying there. I like that statement a little bit better. We're looking at a strong base. So ideally, you'd say strong base first and then go to the reagents. Okay, so you're right. We want that strong base. What's happening in the next Yeah, we could do that. What's happening in that next one to the right? We're doing an oxidation reaction. Why do we not oxidize at those positions? Let's say this is chromic acid.
That's not part of an aromatic ring. You have to get the benzylic position.
We need the benzylic position, which is really, really important. So that's where I would say your statement was correct. It needs to be benzylic for it to react. Why are those orange dots not reactive? Because they're part of the aromatic ring. Right? They're within the aromatic ring. That's super, super stable. Only when we push that one extra carbon further away, now we're at the benzylic position, that can react with our chromic acid. Does that make sense?
Yeah, I think that's what I said.
You started to say aromatic ring first, and I didn't like that statement.
No,
That's
yeah,
all
I
it
was
was.
saying that it's now part of the aromatic ring, and you have to get the benzylic position.
Okay, yep. I agree. You are right. I was wrong. Last one. What happened in that last case? What's that? We did an oxidation reaction again. Okay, except being original, we'll shift to using the permanganate. You might see hot, concentrated acid, conc H₂SO4. Okay? Questions about that? I guess we're going to go ahead and call it there because that's 55. Actually, yeah, let's just be nice.